Everyone. Hello, everyone. Good afternoon to my fellow Europeans. Good morning to those who joined us from the Americas, and a late good evening or very early good morning for those joining from Asia. This is the International Space Institute, Space Science Institute's Game Changer Seminar Series, and I'm saying hello from Bern, Switzerland. Where we look at missions, where we look at themes and ideas about the solar system, the universe, and our terrestrial environment. And today we have a talk about terrestrial planetary seismology by Philippe Lognonné, the PI of the seismometer on the InSight mission. And next week we have Alessandro Morbidelli speak about the formation of planetary systems. Now, if you want to stay apprised of the seminar and other ISI activities, consider subscribing to our newsletter. You find the link to the newsletter at the bottom of any ISI webpage. And on the webpage, you find the recordings of these seminars. So all of the seminars are recorded, and the up to 30 now are available for you to download and listen again, or listen for the first time if you missed the seminar. It's my pleasure to introduce my friend Philippe Lognonné as the speaker of today's seminar. Philippe, as I already said, is the instrument principal investigator of the seismometer, the SEIS experiment on the NASA InSight mission to Mars. He is also a professor of planetary geophysics at the Université de Paris and performs his research at the famous IPGP, the Institut de Physique du Globe de Paris. He's also a senior honorary member of the Institut Universitaire de France and a fellow of the American Geophysical Union. And just the other weeks, he received the Prix International d'Astronautique of 2021 of the Société Astronomique de France, and with a lineup of famous pioneers of space sciences. And I'm very thankful to him that he will be here today and explain how terrestrial planetary seismology, in particular InSight, changes our view of planets. Philippe, thank you very much. The floor is yours. Let me just say before I give it over that for the question and answer, we invite you to use the chat channel, in which case I will read your question to Philippe, or you raise your hand and speak for yourself. But now, Philippe, the floor is yours.
Thank you so much. Thank you, Tilman, and thank you to EC to make me the pleasure and the honor to share with you the very exciting time in planetary seismology. Before to start, so you see a long list of names, and more important, at the end of the list, you see that list is even not finished with this page. I want to say that everything I will show you is resulting from a lot of collaboration I made before InSight when I was working on moon seismic data analysis. And of course, I made after the start of InSight with all the InSight SAIS team. So therefore, all the work is really a teamwork, and I am here only the speaker of that very large, very bright, and very innovative team who is now processing the data after having taken their weekends, their free time to deliver on time the SAIS experiment and also the InSight mission. So thank you to all. And so I will try to give you in short, in about 45 minutes, 3 success stories in planetary seismology. I say success story because we end up with data. Of course, I will not speak so much on that, but we all need to recognize that the first seismic, the success story in planetary seismology was on Earth. It started something like 140 years ago with the first detection with the instrument of a seismic signal. We know that China had built some type of seismic detectors, but it was not recording the signal, but it was made many centuries ago. But 140 years ago, from Germany in Potsdam, we saw that record, which was related to a quake in Tokyo. very rapidly after, in a way which was in some way very close from what was made in quantum physics. The data were able to demonstrate that the theory was correct. So we saw P wave, S wave, surface wave in the seismogram. This was made theoretically before, and it was made by Oldham by the end of the 19th century. And very rapidly then, the discontinuity between the crust and the mantle of the Earth was found by Morovici in 1910. Then Oldham detected the core. It was first made in 1906. And finally, Inge Lehmann was able to detect in 1936 the inner core. So you see something like 40 years after the first record, all the Earth was mapped down to the inner core. And of course, the detail were mapped later by a seismic network. Now we have many, many thousand on the Earth. So we have more than 20,000 stations. We do record seismic wave. We do record seismic noise. We understand the coupling of the atmosphere with the Earth. And we start to see all the detail of the Earth in terms of 3D lateral variation. So therefore, this was the starting point when seismologists in the 60s, including Frank Press, proposed to redo the same success story on other planets. And this started very soon after Sputnik 1. You might remember that in 62, so Ranger 3, the Ranger 4, and the Ranger 5 lander sent by NASA to the moon had all a seismometer on board. The seismometer was located on the top of the spacecraft on this big balsa ball, which was supposed to be ejected just before the crash. So therefore, almost 5 years after Sputnik 1, seismology was in planetary science, ready to discover the internal structure of the moon. The 3 Ranger spacecraft all failed, and we had to wait the end of the 60s in 69 with Apollo 11 to get the first seismometer on the moon. And here you get this phone call of Nixon.
From the Oval Room at the White House. And this certainly has to be the most historic telephone call ever made.
Okay, just after the phone call, in fact, the astronauts were starting to do science. And then they deployed very rapidly a seismometer. This was a solar panel powered seismometer. And this seismometer was able to work more than 1 month, in fact, and it stopped to work the day after, the lunar day after. So just after, with Apollo 12, Apollo 14, Apollo 15, Apollo 16, other seismometers were deployed. All were powered by radio generator, so isotopic generator, RTGs, and therefore this was able to operate from 69 until the end of September 77, when a command was sent by NASA to stop all the activity of the seismic network. And in addition to that seismic network, laser reflectors were deployed, heat flow measurements were made, magnetometers were deployed, 1 gravimeter was deployed at Apollo 17 with Apollo 17. And therefore, all the geophysics was able to be used on the moon to get the internal structure of the moon and, of course, its interaction with the solar wind. So this, the first discovery of this was to detect and to detect many moonquakes. So here you have one example of a simulation, and all the references for all the source can be found, in the text. And at the end, I will give you internet access to all these papers through the site of the SACE experiment. So what is important to see is that many quakes were detected on the moon. In the 7 years of operation of the network, more than 13,000 events were detected. Something like about 1,000, a little less than 1,000 impact, many deep moonquake, and something like 30 shallow moonquake. So here you have the typical seismicity of the moon in terms of number of events on this axis as a function of the amplitude there. And the key point to have in mind is that the displacement of all these moonquakes are very small. To give you some idea, here you have the data in digital units, but you have to see that 2 digital units have the dimension of the atom of helium. So therefore, 1 digital unit is something like 0.5 half an angstrom of ground displacement. So therefore, the moon is very active in terms of frequency, but it is weakly active in terms of ground displacement or in terms of release of seismic energy. But nevertheless, you know, if you put a seismometer on the moon, you will probably detect much more events per day than in France, which is known to be a very weakly place, even if we do have some activity, of course, in the south, in the Pyrenees. Anyway, what was detected on the moon was this shallow moonquake, very little, something like 30, very active deep moonquake activity, which is related to the Earth tide, and of course, many impact just because there is no atmosphere on the moon, and all the impactors are hitting the lunar surface at speed between 10 to 30 kilometers per second. So with all these data set, seismology can be made. I want to recall you that when you want to do travel time seismology, what you need to do is you need to pick up the arrival time of the P wave and the arrival time of the S wave. So this is what you have here on this example, where you have the record from Apollo 12, Apollo 14, Apollo 15, Apollo 16. And with this record of travel time, so you are able to mathematically determine the location of the quake and the propagation speed of both the P wave and the S wave. So therefore, with this data set, so you can get one apparent velocity of the wave. Of course, when you start to get many quakes, so you will have different epicentral distances between the station and the quake. And then you will be able to get this apparent velocity as a function of depth. And after that, you need to use a mathematical approach like inverse problem or Monte Carlo modeling to find or to match the best model fitting the data. So here you have this typical data set. And here you have one example for all the data sets recorded on the moon as a function of the epicentral distance here, with here the time, and the blue line are the blue line for the P wave arrival time, while the green line is the arrival time of the S wave. So what you immediately see is that the signal is very diffuse. So you see that the duration of the signal is not something like a few minutes, like it might be the case on the Earth, you know, but it is the duration of the signal might be almost 1 hour, even for the largest moonquake, 2 hours. And this is related to the very intense diffraction of the moon. This diffraction was recently modeled very well by Keisuke Onodora, who is finishing his thesis between Japan and France. And you see that in this modeling where we try to model the propagation of the wave, when we play with the random lateral variation of the media, we start to destroy the structure of the wave, and we can generate, instead of very nice arrival like this, we start to generate what we call in seismology the coda. So therefore, this is why it was found very difficult to work with the amplitude of the lunar seismic data. Most of the work was made with the travel time. So The other point of Apollo was the fact that the network was mostly on the near side of the moon, near the equator of the moon, mostly for ballistic reasons associated to the human mission. And also, and because of that, you know, it was able to see only this limited part. And the last point is that, you know, depending on the distance, not everywhere was detected in the moon. So here you have the rays as a function of the type of rays. So the blue one are the deep moonquake, the green one are the shallow moonquake, and the red rays are those related to the big impact. And this is for the data set of located event. And you see that at some depths, something like 500 kilometers, we do not have so much coverage. And of course, you know, in the very deep moon, we were not able to get direct wave, even if reflected wave were detected later. Okay, so how to proceed? Of course, I talk, okay, I made a rapid description of the classical techniques, which is based by using the P wave and the S wave arrival time. But what was done also in seismology more recently was to work with what we call the crustal conversion. So the idea is that if when you have a wave arriving like this, you know, that wave will be converted at the crust. And therefore that conversion you see will bounce here, will bounce back here, and will go back there. And therefore you can get at the same location several arrival of seismic wave, and the difference of travel time tell you something on the thickness of the crust, or if you prefer, on the depth of the interface here. And here, courtesy from Brigitte Knappmeyer and Run, you have one example with a simulation where you see this direct wave arriving. You know, it will be converted at the MOHO there, and you know, you see all this later phase can be used to match and to detect and to constrain the crustal thickness in this case. So therefore, this was used on the Earth, and at the beginning of 2000, when all the data set which was recorded by Apollo was put back by JAXA and IRIS in new seismological format, all the scientific community was able to reprocess this data set and to work on this data with the modern techniques, including the receiver function. And Lev Finik was able to process the data to identify the precursor of the wave, which is associated to the conversion of a S wave into a P wave. And because it is a P wave, the P wave is faster and therefore arrive before. And then was able, you know, to get this differential travel time between the S wave here and the P wave, the conversion from S to P wave arriving something like 8 seconds before. Now, the point is that this travel time is just a travel time, and because it is a travel time, so you can change the structure, the velocity, and you can change the thickness in the same way, and you will end up with the same travel time. In other words, you know, if the velocity are very slow, so you just need a thinner crust to get the same travel time, or if the velocity are faster, so you can get the travel time with a larger crust. And therefore, this tell you that here you see that travel time will match with either a 30-kilometer crust or a 60-kilometer crust. The 30 being obtained when you have relatively low velocity in the upper part, and the 60 being obtained when you have relatively large amplitude. But on the other hand, so you see that most likely you can play a little bit with the amplitude there compared to here. And that amplitude was already suggesting that probably the crust is thinner than the 60 kilometer, which was proposed by the first seismologist working on Apollo. And in fact, the key point here is to get additional constraint telling you something on the velocities. And this was made a little bit later by Grail. Grail was able to detect and to find that the upper part of the crust has a very large porosity. In other words, that contrary to the Earth, we expect to have relatively low densities. We expect to have relatively low seismic velocities. And therefore, this was pushing more on the thin crust than on the thick one. And finally, you know, that work was completed by combining impact seismic travel time data with gravity data. And this is what you get. This is almost the final state today of our knowledge of the thickness of the moon, where you do have here the thickness seen by seismology, you know, compared to the thickness seen by Grail. And you see that in many cases, so the two thickness are okay. So therefore, we have that constraint where we also see that seismology need also for that type of analysis, other type of geophysical data, including gravimetry. So of course, with the travel time, the same type of analysis were made for the mantle. But we have to say that at that time, you see, when we compare all the literature, so paper made by Amir Khan, paper made by our team in IPGP, paper made by Yoshio Nakamura, together with analysis made by geochemists from Kuskov and other colleagues in Moscow. In fact, all this type of determination agree roughly, but it is very difficult to use this to get very fine constraint in terms of mineralogy. So most of the time, what we need to do is we need to use these seismic velocities to freeze or to make some hypothesis on the mineralogy, and then to see what will be the consequences in terms of velocity. And probably we will need to go back to the moon to have a precision comparable to the one we can have on the Earth with the PREM model made by Don Anderson. So, and I will finish the moon with, of course, the most interesting part of the moon for many planetologists. And I am sure that you will have some discussion next week on that, and especially on the lunar formation. But one of the big questions, which was still missing by the end of 2010, was the size of the lunar core as seen from seismology. So at the end of the last century, so in 1999, we already had some strong suggestion based from the analysis of the Clementine data that the core of the moon was highly conductive, so and most likely iron. And a little bit later, you know, from the libration monitoring data, Williams at GPL was able to determine the fact that we do see some a delay in the libration, which is most likely related to some type of viscosity, which must exist somewhere in the moon. And because the moon has no ocean, you know, the only place where we can have some type of viscosity is between the mantle and the core. So therefore, by the end of 2000, the beginning of 2000, the beginning of the 2000s, this millenary, we had very strong feeling that we had a core made of iron and most likely liquid. But the demonstration was not made by seismology. So therefore, two teams, one based around Rafael Garcia and the other based with René Weber, were decided to reprocess the team. The work were made at the same time. So therefore, this was really two teams working together almost at the same time, even if the paper from René Weber was first published. And the idea was to take this deep moonquake and to look for wave reflected by the core arriving at the surface. And again, the idea is to compare this wave with a direct wave. So therefore, you do this mathematical processing called deconvolution. So you try to identify where you get the best waveform fitting associated to this converted phase compared to the first one. And that gives you the travel time, and therefore it gives you the depth. At the end, this was made by a stack on all the data. And here you have the results, and these are the results shown by Rafael, made by Rafael Garcia. So here you have, so basically what you will get if you have a full noise, you know. So this is the 1 sigma noise level. So here you have the 2 sigma noise level. So therefore, anything which is between 1 sigma and plus 1 sigma and minus 1 sigma might be noise to the 1 sigma level. And what is very interesting is that you get this peak of energy there, which is exceeding 2 sigma, which tell you that there is something in the structure of the waveform which can be compatible with a reflection of wave from a core with a radius of 400. And therefore, this was the third way to determine the core thickness, the core size of the moon. So today we can clearly say that both geodesy, magnetism, and seismology have demonstrated that the moon has a core, that core is liquid, and that the radius of that core is somewhere between 350 and 400 kilometers. So the 2 papers in the literature are first proposing this structure. This is the work from René Weber with a solid inner core, a fluid outer core, and a partial mate layer. And the work made by Rafael Garcia is proposing a fluid outer core, and he was not able to detect a signal from below. But both are converging to this fluid core. And the last piece of information was the one on temperature. So Amir Khan made some work on determining from the inversion of seismic data the temperature profile of the moon. This was also made with the inversion of the magnetic data. So in IPGP, we made a similar approach, even if more simple, by inverting the temperature with a frozen mineralogy. And when you compare all this analysis, so you end up with this estimation of the temperature at the bottom of the mantle, which tell you that because the core is fluid, most likely it cannot be a pure iron core. It could be ilmenite, but it is most likely a core with some light element, because this is typically what you will get with the temperature constraint. So therefore, this is a picture we have from the moon, and this was the success story 2. I hope that it will continue. We hope that it will continue with a new mission to the moon. You have to see that what I've shown you is basically to do science with this type of data. And what the seismometer today can do is to record this seismogram like this. So therefore, you see here the fact that Apollo was working with a low resolution instrument. So here we get very modern instrument, and all the modern instruments are able to provide much superior data. So it will give us new phases, including from the inner core, and it will give us much more data. Probably we will be able in 1 year to get much more than what Apollo was able to get in all the 7 years of operation, just because of the much better resolution and sensitivity of the modern seismometer. Okay, now I will, of course, do present you the third success story. And this third success story in planetary seismology is InSight. So, and I really want to address my congratulations to Bruce Bannert, who was able to convince NASA to fly this wonderful mission, and also to make that wonderful mission so nice in terms of international collaboration. It is really a big pleasure to work with here. So with this mission, something like 50 years after the deployment of Apollo 11, and something like 130 years or more after the first seismometer on the Earth, seismology was able to start on Mars. I have to say that seismology was also done before with Viking, and Viking had the seismometer on the deck, like the seismometer of InSight just after the landing. But because of also the very nice paper of Don Anderson, who was able to explain what you need to do and what you must do in order to succeed after the relatively failure of not Anderson, but of the Viking seismometer, we were able to design the mission and to force all the engineers to find the best way to deploy the seismometer on the ground. And we were very lucky to do that because if we had to stay on the deck, you know, we might be in a situation where we will be much more sensitive to Viking in terms of wind noise. And this gives you a comparison where you have the wind speed here, and here you have the seismic signal in Viking unit. So you see that Viking is a red line, and in fact, InSight is something like 2 times more sensitive. So it is the green line. So therefore, we were lucky to really land. And why it was the same, just because, you know, the 2 lander had feet, and the feet were some type of oscillator, and they had they were in the front of the wind, so therefore everything was vibrating. So therefore, for SACE, the final and the success, the real landing was the one made by the technical team when they took the seismometer on the deck and put it on the ground. And I want to share with you that unique time in planetary exploration where you discover this successful landing on the planet.
Oh.
And indeed, everybody was very happy because it was, we knew that it was a critical time of the mission to have that seismometer on the ground. So again, the seismometer is very much protected. So the seismometer, the sensor are there. So they are protected in a series of thermal protection in order to have the very quiet or to reduce as much as possible the impact of the environment on the data. So what look the seismic data? So I just show you this an example of data. So these are 3 days from 19, and you see that every day, you know, the data, they look almost identical to the day before. So here you have the spectrogram, and what you see is that when you have -200, it's basically tell you that the ground acceleration is 10 minus 10 meters second square per square root of Earth. So which is roughly the gravitational attraction of your portable computer, your PC computer. You know, if you take your PC computer and you move it from something like 20 centimeter distance away, it will generate a gravitational attraction equivalent to this type of acceleration. I do not suggest to do that because you will lose my seminar, and you will record nothing. But you have to see that the blue color means very, very low gravitational ground acceleration. And also I have to say that all the data you will see here can be downloaded. So therefore you can reproduce this analysis. You can get access to the data. and just follow the link and the guideline you will find in the link. So the first point is that we are on Mars, and if we were on Earth, so basically everything which is red on this figure will not be seen. So therefore, to be short, most of the signs I will show you will not be possible. So all the signs we have made on Mars was made possible because the seismic noise is much less than on the Earth. And this is illustrating that seismic noise. Here you have the frequency. So this is 0.01 Hertz, so 100 seconds. So this is 10 Hertz. So we go up to 50 Hertz because our sampling rate, maximum sampling rate is 100 samples per second. And what you see here, so is you see the noise level during the night where we are very close from the sensitivity of the instrument. And when the day is rising up, the sun is rising up, we start to have more and more atmospheric noise, and the noise is going up, and then the noise go back during the night, and this is repeating every day. So this here are the seismic noise of the Earth, so which means that you see that between that seismic noise on the Earth and here, so you have almost 3 orders of magnitude, something like 500. So which tell you that we can detect quake with a seismic moment, something like 2 smaller than on Earth. In other words, when we believe, okay, because we can detect in a global way on the Earth quake of magnitude about 5, so we can do that detection with quake of the order of magnitude 3 on Mars. So therefore, this was really the success of the mission, this very high sensitivity and low noise. So during the daytime, we nevertheless have a lot of noise, and that noise is mostly associated to the activity of the atmosphere. So you see that on the pressure, you have this burst of energy there, almost vertically, so which means that this is almost like a Dirac function. And in fact, that Dirac function is something you will see on this record of the pressure. So this is what we call a pressure drop. The pressure drop is sometimes associated with what we call a dust devil. And here you see the dust devil moving on the ground. And the depression in the middle of the dust devil is generating a ground deformation. And that ground deformation is recorded by the seismometer. Here you have a record on the vertical axis, and here you have a record on the horizontal axis. And these are most of this spike of energy during the daytime. So this is interesting if we want to study the subsurface, but it is much less if we want to study the seismicity of the planet, because basically it means that we can have a very good detection capability only when the atmosphere is steady, is quiet, and this start to occur at something like 4 o'clock. I will go back on that later. But this is something you get here. So you see that here on this record, which is a summary made by the Mars Quake Service in ETH of the operation of the mission from Sol 80 to Sol 800, so which means until March this year. So you see that most of the daytime where you have the yellow color, it is very shaky, you know, and you have a ground acceleration up to minus 140 dB, so 10 minus 7 meters second square, while it starts to be low noise after the sunset. The sunset is here, so here the wind decreases, it starts to be very low noise, and we have then a window where we can really detect a lot of activity. And of course, I will detail that more in the following slide. So this is really the key point. So if we want to go back sometime in the future on Mars, even if we have made a lot of effort to protect against the wind, these efforts were not large enough to completely remove the wind effect. We are still detecting most of the day the effect of the wind on the ground mostly, and also a little bit on the lander. Okay, so the seismometer was put on the ground in February 2019. And very rapidly after, in April, we were lucky to get our first quake. So this was a high frequency quake. That high frequency quake was a quake which might be detected on the Earth. So again, here you have the spectrogram, and all the black part are where this cannot be detected on the Earth, but you see that it was detectable on the Earth at a few hertz frequencies. And you probably have got the sound of this quake. You have it. And the quake is here. And this is not a quake, this is just an activation of the robotic arm of the lander. And we were lucky to have it a few minutes after. Okay, so this was the first quake. Then we got, this was a quake which looked a little bit like the Moonquake with a significant duration in terms of coda. So you see here the coda has a duration of something like 15 minutes. It is definitively not the 1 hour of the moon, but there is definitively also diffraction and a relatively low attenuation compared to the Earth, even if compared to the moon, we see already that the attenuation is a little bit larger. So a few months after we got our first low frequency quake, and here it was, of course, very nice for us because for the first time we were able to see a P wave arrival and an S wave arrival, but we did not detect a surface wave. And with the P wave and the S wave, we were able to start to estimate the distances. And that quake, which was detected on Sol 173, was also clear enough to be able to detect the azimuth of the quake and therefore the direction. So with everything now, I can give you some type of summary of everything which was done after this 800 Sol of activities. So as said, on March 21, we detected more than 500 events. We detected more events, but the additional one are high frequency one, which might be more related to thermal cracks in the near vicinity of the lander. So most of these quakes have a magnitude, about 50 of these quakes have a magnitude between 2 and 4, and all the other one, the 451 are probably smaller magnitude events. So, and here you have the description of this activity, and you have all the detail in papers made by John Clinton, Ceylon Savas, and all the colleagues working under the guideline of Domenico Giardini at ETH with all the team, especially young scientists working on what we call the front line. So a group of scientists who is processing the data every day to make this catalog available to the community. So we did not detect any clear signal associated to a recent impact or even recent landing. And most likely, all the impact we have seen today were too small. So this gives you the distribution of the quake identified as a function of the noise. And again, so you see that thanks to this low noise window, we are able to detect quake. And it was difficult to detect a quake during the noisy time, even if you do see some large event, on some places associated to relatively strong event. So, sorry. With all these data sets, the first point is that we have been able to locate the largest quake near Cerberus. And we have been able, and this was made by Nienke Brinkmann, Domenico Giardini, Melanie Drio, Rafael Garcia, and others. We have been able to do a location of the quake. There is an activity ongoing on determining the seismic mechanism, and to relate that seismic mechanism to the fault system. And you see that the direction of the inversion fits relatively well with the fault system. And of course, so we work better and better, and we understand better and better the noise. So now we start to process the noise to be able to reduce the noise by decorrelation. Of course, we use that noise to see if we can detect other type of events. So we believe we have detected also infrasounds. And something surprising, which you will find in a paper made by Simon Steller, is that when we got eclipse of Phobos, we are able to detect the ground temperature variation. So therefore, the tilt associated to the temperature cooling of the ground. And this gave us additional constraint on the thermoelastic properties of the ground. So, but I will jump a little bit. But we still continue to have some not problem, but we fight against the noise in order to be able to reduce it. What is interesting is at high frequency, so we do see a vibration of the lander. So therefore, and this is where you have this yellow line. This is something which needs to be taken into account in any analysis, especially in noise analysis. And this is why at that time, you know, the project is trying to reduce the noise by burying the Tether, which is located there with the scoop. So therefore, we are taking some sand, and we are putting the sand, you know, on the Tether, and we hope that with that process we will be able to get even better data in the next months and year, mostly because we do see some thermal cracks during the cooling time of the seismometer. We want to suppress. Okay, now I will finish my presentation with the finding related to the internal structure of the planet. So I will start with the subsurface. So a lot of work was made by using the pressure drop. So you see that signal I've shown you during the daytime. So, and the idea is to try to feed this signal with the elastic loading of the ground. And in the feed process, so you can invert the amplitude, the phase, and the shape of the signal to get the structure of the ground. So this is what we call the compliance. And now we are able to get this type of profile, you know. It was first made for 20 meters, and now we are able to go down to 100 meters. And these are papers in progress. So for deeper in the crust, so we have been able to identify first a conversion of body wave rising up, you know, converted into, you know, other body wave. And this conversion tell us that the first 10 kilometers of the crust have some type of discontinuity at about 9 kilometer depth, and they have very low seismic velocities. And probably the only way to understand these very low seismic velocities is either with high porosity and or with some type of alteration of the crustal material, which might be just the cumulative effect of millions of years in the past, you know, of water circulation. I am not saying that water is circulating in the dry upper crust, but I am just saying that this type of low velocity are reflecting a past activity like this. So, and this also we were able to compare seismic data on Mars, on the Moon, to get some constraint on the attenuation. And that attenuation put Mars somewhere between the Earth and the Moon. So we have definitively much less attenuation than on the Earth, but we have more attenuation than on the Moon. So which means that probably with some fluids, some layers of volatiles, okay, we will be able to explain this type of attenuation with quality coefficient of the order of 500 rising up to a few thousand as a function of frequencies. And now much deeper, we have been able to detect converted phase. So what we call the bouncing phase, it is a S wave bouncing at the surface, bouncing 1 time, 2 times. This can be made by the P wave, this can be made by the S wave, and we have also searched for core reflected wave, again in a very similar way as what was made on the Moon 10 years ago. And this succeeded very well. So basically, we have been able to detect by, and this is one example of the techniques. This was made with different techniques. This was made by Zhongbo Zhu in this example. So, and the idea is to look for phase matching, where we can match a phase with the direct phase, which is the red one. And this phase matching tells you that there is a reflection somewhere there at about 700 seconds of arrival time after the P wave. For SACE, first again, I want to thank all the team who gave me the privilege to show you and to show you these very exciting results. Now we have the data on Mars. We believe that the data will continue to be there. This data can be used by any of you. You know, you just need to go on this site, you know, and to get them. You have all the information, so you can have much more information if you go on the SACE website, where you will have all the paper put in open archive. And we hope that this will continue in the next years. And in terms of planetary seismology now is back in planetary science. It is back on Mars. It will be back on Titan and on the Moon, just because we do have a seismometer on Dragonfly, and we will have, therefore, after 2030, some data, seismic data on Titan. We will have, again, a seismometer on the Moon, as the Chinese space agencies has decided to have a seismometer on the Chang'e 7 lander. And I hope that with the Kazachok lander and the Russian seismometer on board that lander, we will have a second station on Mars sometime soon. And we might even have some type of very nice network of screw stations on Mars operating after the landing of ExoMars 2 Kazachok lander. So therefore, seismology start to be a rule. Therefore, I hope that this deployment of seismic network of the solar system will continue on its way, and that all the space agencies will consider very seriously helping us to get access to this exciting data of the interior of the terrestrial planet. Thank you.
Thank you very much, Philippe, for this fascinating talk. It was a pleasure to listen to all these results and the data from the Moon and Mars. We're running a little late, but we have questions here already in the chat. But I just let me remind you that you can, if you have questions, you can either put them in the chat and I will read them to Philippe and answer them, or you raise your hand and then Willie will give you the floor and we switch between the two as they come up. So I start with Bernard Foin saying that there was a great start with moon seismology. And did you have rays from impacts or shallow quakes probing the South Pole Aitken giant basin, including its crust thickness close to 0 at some points? So do we have these data and results?
Okay. The question is, did we detected with Apollo impact on the South Pole SPA? Unfortunately, the answer is no. Apollo was not able to detect impact on the South Pole. Apollo was nevertheless able to detect a very large shallow moonquake, and it's turned out that one of the largest moonquake which was detected on the moon is very close from the South Pole. So for very strange reason, you know, space agencies are considering to go in a place where we detected one of the largest magnitude for something quake on the moon.
Okay,
So,
I'll take two more questions from the chat, and then we go over to the microphone. So the next question is: you have more sensitivity to seismic waves on Mars, partly because there are no humans shaking things up with their vehicles and explosive devices, and because the atmosphere is less noisy on Mars. This is an easy one, Philippe.
Can you repeat the question, sorry?
Well, the question was whether the low noise on Mars was due to no humans, yes. You know.
Alors, yes and no. In fact, the low noise on Mars is mostly due to the lack of ocean and wave in the ocean. So most of the noise on the Earth is related to the ocean activity and the waves. So this is what we call the microseism. And this is most of the noise. Of course, in high frequency, human activity is making some noise, but it is much less than the activity of the ocean. So unfortunately, what we can say is that there is no hidden ocean on Mars.
Okay, nice talk. According to the figure of Marsquakes events distribution, so it's 80 to 800, it seems that almost all the events are basically in the wind season before Sol 400. Is this the wind effect? If it is, how can we evaluate or remove the wind noise?
Okay, so basically the question is why we detect all the quakes there.
Yeah.
Yes. In fact, unfortunately, the answer is simple: is that we probably detect all the quakes there because yes, the quakes you know, during that time, you know, are hidden by the noise. So, and this is why there is a very strong effort of the team to try to better understand the noise in order to remove it. But I have to say that at that time, you know, we have not yet succeeded in making a good noise decorrelation.
Okay, let's move over to the people that raised their hands, and the top on the list here is by the name of Loyq. I don't know how to pronounce that. So Loyq, please pose your question.
What? Can you hear me?
Yeah.
Yes.
Okay. I saw in your talk related to the lunar, you have the magnetometer, and you also have the magnetic data. I just wonder, what's the typical field strength for the moon? And also another question for the Mars, do we have the magnetometer for the Mars?
Yes. Okay. So the answer is okay. I am sorry. I am not a very good expert in magnetic field. So therefore, I will not give you the field strength. But what I can tell you is that magnetometer on the moon, okay, we found that during sunset and sunrise, so we can detect, okay, we detected some signal on the seismometer because of the impact of the solar wind on the coil of the seismometer. And of course, you know that magnetic field was also detected when the Earth was going through the magneto-tail. On the other hand, on Mars, yes, we do have a magnetometer. We put a magnetometer on inside at the beginning, mostly because we wanted to ensure that we will not detect a noise associated to the interaction of the magnetic field with the spring of the seismometer. The good news is that that was not detected, and the second good news is that now you have very interesting magnetic data. I invite you to have a look on the paper of Catherine Johnson, who was published in Nature to get more detail on the magnetometer.
Okay, next question.
Are you saying for the moon, the magnetic field is due to the magneto-tail of the Earth, and also due to the solar wind magnetic field? what
Yes.
would be the intrinsic magnetic field of the moon?
Okay, so this is my understanding, and then I can understand. Okay, I can imagine that a colleague, expert in magnetic field, will tell you that there is some DC remnant magnetic field. There is a lot of work, but I'm sorry, I am not expert on that. I know that people like Mark Vizorek work a lot on this topic.
Okay, let's go over to Ninto. Ninto, please.
Did you hear me?
Yes.
Oh, it's perfect. Thank you, Philippe, for this terrific talk. We really enjoy it, and give the feeling that we have read a lot of papers to catch all this new information. So I would like just wonder if you can tell us something about the coupling with the atmosphere on Mars, because I suppose that it was also atmospheric instruments and in the insights. And so I wonder if this 10 kilometers layer that is really attenuating the signal is reducing what we expected as coupling with the atmosphere.
Okay, so we do have a coupling with the atmosphere, and some analyses were made by Rafael Garcia and Leo Martir and his team, on trying to detect in the seismic signal events which might not be related to interior activity, but to atmospheric activity. So at that time, we do believe that some of the events might be infrasounds. It is a minority of them, but we have some indications that there is indeed some infrasounds. This is for the coupling from the top to the bottom. Okay. If you want to discuss or to ask on the coupling from the bottom to the top, as it is on the Earth, then of course the density of the atmosphere of Mars is so small, and also the ionosphere on Mars is so small that this is really something which can be completely neglected. There is no the signal which might be generated by a quake, will not be detected in terms of coupling by the pressure sensor. So we do.
Sure, but I wonder if the coupling is reduced compared to what we expected by previous simulation.
No, I think that this okay. So this. So you address an interesting question, which is, to do ionospheric or atmospheric seismology on terrestrial planet. So definitively, Mars is not a good candidate. On the other hand, I had no time to discuss on Venus, but Venus is a perfect candidate. So therefore, for Mars, there is no prospect to do that. We have some idea, as you might know, for Venus, but this might be the topic of another seminar.
Sure. Thank you. Thank you so much.
Okay, Gloria Königsberger. So,
yes, I see Andrei Lazarevich. So,
okay. Sorry, but now we haven't. Okay.
Yes, I want to say that, I learned a lot from the paper of Andrei, who was on the wind sensitivity of Viking, and it gave us a lot of very important constraints to build and to design the mission. So I will be very happy to answer the question of Andrei.
Well, good afternoon, and thank you.
I had actually called Gloria first, but
sorry, but
but now we have Andrew. So Andrew and then Gloria.
Okay. Sorry, Gloria.
Sorry about that. This is Andrew here.
Yes.
Your talk was very interesting. It was illuminating on a lot of things. It's very helpful. Did you have, prior to landing, a concept of any expectation of impact detections? And are you surprised by the fact that you didn't have any impact detection to date?
Yes and no. In fact, we work before the landing on the impact a lot, and we end up to the conclusion that most likely, we will detect impact only if these impacts are larger than 10-meter diameter. And at that time, thanks to the help of our colleague, working on IRISE, working on all the imager of NASA and ESA, a lot of activity were made, but no big crater, larger than 10 meters was detected nearby. So in some way, it is not a surprise. It is in some way disappointing because we wanted to have a few of the impact, but at that time, nothing strong occurred. But it is not really a surprise. I will be more badly surprised if we see a crater of 10 meters or more, and if we do not see signal. At that time, it was mostly 5 meters. Okay, crater of the order of 5 meters. And there is a big difference between the two.
Well, here's hoping that you do get an impact. That would be a wonderful new piece of data. Thank you very much.
Thank you.
Okay, Gloria, it's you now. Gloria?
Hello?
Yeah.
Hello.
Okay, I was muted, sorry. Yeah, I was wondering, I missed the connection between the eclipse of Phobos and the cooling. That's one question. And the second question is whether you have a value for the viscosity on the moon.
Okay, so yes, unfortunately, I do not have a figure here for the cooling. But what is happening is the following. So when we get the cooling of Phobos, the ground temperature is decreasing. And that decrease of the temperature is reducing the ground temperature, okay, by definition. But basically it is decreasing everywhere where the sun was acting. So therefore, below the solar panel, it is not decreasing because the solar panel were in the shadow. So therefore, what is happening is that when the eclipse occurs, all the ground which was illuminating by the sun has a temperature decreasing a little bit, while the ground which was not, illuminated by the sun is keeping the same temperature. And that differences of temperature generate stresses in the regolith, and the stresses in the regolith generate tilt of the ground of the order of 10 nanoradians, something like that. And this is what the seismometer is detecting.
Okay, thank you. Thank you.
For the viscosity, I am afraid that the viscosity, okay, so I think that there is probably some delay, okay? And if you go to the paper of Williams, you will probably have some constraint on the viscosity, but I do not have the number in mind at that time.
Okay, thank you very much.
All right, so Bernard Foin was actually raising his hand, but now he's in the chat. Exciting science results, bravo. How do you expect the proximity of Elysium Mons volcanic complex to likely influence the inside site, local deep subsurface and tectonics, and what could have an imprint on size data?
Okay, this is a very interesting research question. And the question, okay, my understanding of the question in terms of activity is the following. Okay, so yes, sorry. Okay, here we are. So this is basically what we have in Cerberus. And indeed, Cerberus is not so far from Elysium, And we know that Elysium was active in the last maybe 20 million years, So we know that there is some hint of volcanic activity there in the last 20 million years. So therefore, the question is how much that relatively recent activity of volcanism was or is able to increase the thermoelastic stresses in that area, and therefore whether or not the more active seismicity of Cerberus is related to this past activity of Elysium. So therefore, I think this is an interesting question, but at that time we need to work on it. So we need to estimate better how much stresses are concentrating there, how much stress release is can be estimated from the activity. But indeed, I will say that the local activity of that zone is definitively larger than the average activity we had in mind for Mars.
All right, Andrew Ball. Hi, Andrew. Writes, congratulations. Also, I admire your patience. Wow, where is it gone now? Admire your patience since Mars 96. Where to put effort in future missions? More measurements of environmental parameters for the decorrelation, or even better isolation of the instrument, or both?
Okay, so we do know that most of the day temperature is most of the daily noise is related to the dust devil, the atmospheric activity. And this is mostly due to the fact that we are sitting on a very low rigidity ground. So therefore, I think that the top priority for me for any future mission going to Mars to reduce seismology is first to reduce the type of very good thermal insulation we had. Secondly, to keep in mind that, and this is very important to really have in mind, is that you have to see that, okay, yes. Okay, so this is the activity we do see on Mars. Okay, so here you have the amplitude, and these are PST in displacement. So if you prefer, so this minus 200 here is 1 angstrom of ground displacement. So therefore, you need to keep in mind that if you work in ground displacement at a few hertz, and if your seismometer is not able to detect 1 angstrom in terms of ground displacement, you will miss all the activity we detected on Mars. So therefore, this is the first point. You need to have a very sensitive seismometer, and if not, you will just detect nothing. And then you need to find a way to not to be sensitive to the ground deformation because of the atmospheric activity. And the only way to do that is to find a location where you will get access to the bedrock.
Okay, so
but I have to say that if you go on the moon, there is no atmosphere, so therefore you can get very, very high resolution on the moon just because all the problem of Mars disappear, in addition to all the problem who already disappear from the Earth to Mars. So.
Okay, the next question is by Amir Bagheri. There was a recent science paper that the oceans were present in the past on Mars are buried within the planet. Will it reconcile with what we see from seismic data?
It might be, yes, in the sense that what we, okay, so at that time, what we do know is that we do know that the seismic attenuation we do see, you know, is between the Earth one and the lunar one. So how much this is related to water injection in the deep crust, I think it is an open question, but it is reasonable to imagine that any type of water injection which was made in the past will make the lower crust and the mantle less dry than the lunar one.
Jinai Zhang asked, did SEIS detect any tidal signals?
Okay, no, in fact, unfortunately, no. And the answer and the reason is there. One of the reasons is that at that time, we still are working on removing all the thermoelastic signal or noise, if you prefer, especially the one which occur after sunset. And this is making all the the Fourier analysis very complex, especially those looking for the tide signal. So this is work in progress, but we know that statistically longer we will be, better it will be. But the point is that at that time we are only growing as the square root of the time and not more.
Okay, Xing Shi asks, hello Philippe, nice talk. Some moon velocity models suggest a constant velocity for the lunar upper mantle, which may extend to about 500 kilometer depth. So do you think the lunar mantle is isotropic or anisotropic?
I will say that at this time, at this time, and this is on this figure, you see, so this is the knowledge made by all the team, on the moon. So you see that the error bar is of the order of 10%. Okay, the error bar is something like not 10%, so maybe 5% of the signal. So anything which will be closer than smaller than 5% is within the noise of the inversion. So I do believe that anisotropy is not something we can extrapolate from the data set at that time. It will request new data, it will request new mission, and it is probably the same for lateral variation. So if we are able to convince all the space agency of the world to put a seismometer every time they will land on the moon in the future, we will have a beautiful seismic network to discuss that further in detail in 10 years. And I hope it will be the case.
So do we. Okay, we exhausted the questions in the chat. There was a raised hand. I thought I saw a raised hand but it is gone. Anyways, so we're at the end. Thank you very, very much again, Philippe, for this amazing talk and for all the results that you presented us. Thank you very much for listening in. Next week, we will have, as I said, Morbi or Alessandro Morbidelli speaking about the formation of planetary systems, comparison with exoplanets, and so forth and so forth. We'll hope to see you again then. And have a good day and bye-bye.
Thank you. Bye-bye.
Bye.